Hi everyone, my name is Ilya and today I will talk about our new shiny Kotlinx datetime library. But before we talk about the library itself, let's take a quick look at the state of the Kotlin ecosystem regarding working with dates and time. If you target a single platform, you have Platform API at your disposal. If you're lucky enough to target JVM 8, you can use pretty decent Java Time API. If you're not so lucky and still have to work with Java 6 or 7, you have only legacy Java util-date in the platform, but you can resort to third-party libraries. All these single-platform APIs can more or less suit your needs, but if you're developing a multi-platform application, it quickly becomes tedious to work with these specs, actuals, to think about each platform's peculiarities. So there is a clear request to develop something multi-platform that can hide all these platform differences under the cover and provide a unified API. And while we were designing our Kotlinx datetime library, not so in a hurry, I must admit, a couple of community multi-platform datetime libraries emerged during that period. To name a few: Clock, Fluid Time, Island Time. These are pretty different libraries. They support different sets of Kotlin platforms. They have different philosophy behind them. We're not saying that the release of Kotlinx datetime puts the end to all these libraries, because we pursue different design goals. So there's still much room for different ideas in this area. What is Kotlinx datetime library? It's a multi-platform library that supports all major Kotlin platforms. Kotlin JVM, though it requires JVM 8 or higher because we base our implementation on the Java Time API. Kotlin JS, and a variety of targets for Kotlin Native. The design principles behind our library are following. We use immutable types to represent temporal values. A historical perspective shows us that immutability is not a good property for value types, such as dates. Then we strive to provide a minimal API that solves most practical use cases. We'd like to avoid complex class hierarchies in order not to overload our users with a lot of choice, increasing the risk of this choice being incorrect. We design the API in such a way that incorrect or unsupported operations are prevented at compile time rather than failing at runtime. Let's take a closer look at what we are trying to avoid. In this snippet, implemented with Java Time, we have the date of today and we're trying to find the date of tomorrow. One can find that local date type has the plus function that accepts a temporal amount value. We know that the duration type implements temporal amount interface, so we can construct such an innocent-looking expression: date plus duration of days 1, and expect it to give us the date of tomorrow. But if we run it, we'll get something like this: an unsupported temporal type exception with not so clear exception message, unsupported unit seconds. We want to avoid a situation like this, and thus the principle: if the operation is allowed by the API, it should work for reasonable arguments. And last principle is that libraries should be foundational, so that when it becomes mature enough, third-party libraries could provide extensions for it that cover more advanced use cases. Before we meet types that are used to represent temporals, let's talk a bit about flavors of time. First, there's physical time. It can be imagined as a timeline, where one moment follows another moment, and we can represent a point on that timeline using just a number of unit intervals in some designated moment of time called epoch moment. In our library, we have the instant type to represent that integer number of nanoseconds since epoch. We can obtain the instant corresponding to the current moment of time using the system clock. We can construct it from the given number of units since epoch, be it milliseconds or a pair of seconds with nanoseconds, and we can parse an instant from its ISO string representation, something like this. Then there is civil time. It's how people conventionally track time in their locality. For that task, it's much more convenient to use a wall calendar and a wall clock rather than the number of nanoseconds since epoch. Readings of the wall calendar, year, month, and day can be represented with the local date type, and combined with the readings of the wall clock, hour, minute, second, nanoseconds, they form local date time type. We have seen that time can be tracked in two ways, and clearly there should be some way to go from one time flavor to another, right? Suppose you have an instant and want to get a corresponding local datetime representation with convenient date and time components. For that, first we use rules of the Gregorian calendar. They define how many days are per particular year, month, how many hours are in a day, and so on. Using these rules, we can calculate the date and time components, but this will be the components of the UTC time. However, in different parts of the world, each area has its own time that is offset from the UTC time by some number of seconds. A time zone object gives us that offset for a particular location and time. Now you get a time zone, for example, the current system default one, and pass it to instant local datetime function, getting local datetime as a result. The opposite situation is when you have a local datetime, for example, constructed from components, and you want to get the corresponding instant of physical time. For that, you also need to know the time zone, pass it to local datetime to instant function, and get the instant as a result. In this example, if you convert instant back to local datetime, you get the date and time components same as the original ones. So far it looks easy, right? But this conversion has some intricacies related to the daylight saving time. For example, in Spring we have forward clock shift, when the time zone changes its offset from the standard one to the offset 1 hour later. Locally, it can be experienced as if the clock just skips 1 hour at a particular time. We can see that there is time on the local clock which doesn't correspond to any instant of physical time at all. And in case one wants to convert a local date time that lies in that skipped hour with a to-instant function, we need to devise some strategy how to deal with this situation. By default, in this situation, we convert it as if no time shift happened. So we use the offset of the time zone before the shift. If you convert the resulting instant back to local date time, you can see that the time components are different from the original local date time because of this correction strategy. Then in autumn, we have another situation when the time zone also changes from its summer value back to its standard value. Locally, it can be seen if clock jumps 1 hour back at a particular time and goes that hour once again. In that hour, one local time can correspond to two different physical instants. And again, we need some strategy to convert such local date time to an instant. In this case, we choose the earlier of the two possible instants. You can notice that if you add 1 hour to that instant, you get another instant not equal to that with the same local date time components. The important takeaway here is that the conversion from local date time to an instant is not always unambiguous, and the conversion in one direction and in backwards is not always a round trip. Now, when we've met these types to represent temporals, we can ask a question: when is more appropriate to use each of them? First, imagine a situation when you want to log a message and you want to prepend a timestamp when the message was logged before it. How do you do it? You get the current system clock instant and render its string representation before the message. In the result, you get something like this. It's the ISO representation of an instant, and that in the end designates UTC time plus 0 offset. That's a reliable way to represent an instant because it can be reconstructed back from the string unambiguously. But it may be not so convenient if you run your service just in one region, in a single time zone, so it may be more convenient to you to see timestamps in the log local to your time zone. In that case, you can obtain a local time zone, for example, the system default one, and use it to convert your instant to the local date time representation and output that to the log. But from that representation, you can't reliably reconstruct what the moment of physical time it was without knowing the time zone or the offset. So it may be still a good idea to store the offset beside. This allows you to pass this log later and reconstruct the stored timestamp exactly. Then instant can be used to represent a moment in the past, for example, a modification timestamp. Suppose that you're implementing an HTTP server that services client HTTP requests. A client makes a request for a resource. When it already has that resource in its local cache, it doesn't want to download that resource again if it has not changed since the last time. So in order to do that, the client passes an if modified since HTTP header with the timestamp of the last resource modification known to the client. The server then should determine whether or not the resource was modified since that timestamp. To do that, it obtains the value of that header as an instant and then compares it to the resource modification timestamp known to the server. In case if that timestamp is earlier than or the same as the client's one, the server can respond with not modified HTTP status code without sending the resource content. And otherwise, it has to resend the resource content entirely. What about future moments? Instants can be used to represent the future. Consider a scenario when you're implementing now an HTTP client and caching a response from a server. The server puts such cache control header into the response to indicate how long the response can be cached. Max age is the maximum age over cached resource expressed in seconds, and this amount of seconds roughly equals a year. The client calculates the cache expiration deadline by taking the current moment and adding the number of seconds from max age converted to a duration to it, and stores it together with the cached response content. Later, when the resource is needed, this deadline can be used to determine whether the cached content is still fresh or already stale. If the current moment is beyond the deadline, it means that the resource is stale and should be refreshed. Otherwise, the cached content can still be used. What we have seen in these two examples with future instance and past instance is that they do not require time zone for calculations. Such code works in any time zone as long as you use instance, which are basically fixed in UTC plus 0, so it might be tempting to give an advice to define such a rule of thumb. Just use instance everywhere and only convert them to local date time for formatting, presenting the value to a user, and avoid storing moments as data. But would it be a good idea to follow such advice? Let's consider this situation. You're scheduling a meeting in a distant future, for instance, 5 years from now, year 2025, you pick some local date and time components, for example 1 p.m., and construct local date time from them. Now you use the user time zone, Europe, Berlin, in this example to convert that local date time to an instant and store it together with the time zone to some database. And after some time, you read the stored instant and time zone back and get local date time from them to show in the calendar or to display a notification. But imagine what would happen if Europe abolished daylight saving time. I heard some rumors about it. It would result in the same time zone having a different offset in future for the same instant. And if you convert a stored instant to local datetime with that different offset, you get different datetime components. And in the result, the meeting will move to a different time. An hour later, maybe an hour earlier, not a very good situation. So it's important to think about what the source truth is in your application and preserve it when persisting data. In this situation, it's clear that when you schedule something to local datetime, you want to have that local datetime preserved. And it's more appropriate to store a pair of local datetime and time zone instead of an instant and time zone. An attentive listener might notice, if we need to store a pair of local datetime and time zone, why don't we provide something like zoned or offset datetime? What are offset and zoned datetime types? Offset datetime is a local datetime combined with an exit offset from UTC, and zoned datetime is a local datetime plus time zone, but it also contains an exit offset from UTC in order to determine the corresponding instant unambiguously. These types can be convenient in datetime calculations because you have everything at hand, all components that are needed to perform an operation. But these types have some drawbacks. First, problematic compressions. Two values corresponding to the same instant, but with different offsets, are clearly not equal, but it might be unclear which one is greater than the other. Second, in an operation that takes several temporal values, but only one time zone or offset, it's unclear from which value to take that time zone, because each value can have its own one. And finally, if time zone rules change, a stored offset value in zone datetime may become contradictory to that zoned time rules and requires correction. That correction can be done in different ways. Thus, we are avoiding introducing these types until we have a strong use case, which would be impossible without them. Now, when we know when to use each type, let's see what useful operations we can do with these types. Here we have a build running on a continuous integration server. It started at some particular instant of time and lasts for some duration, and we want to find this duration to show it in the UI. We can represent the moment build started as an instant, get the current instant, and just subtract one from another, and get a duration between them in the result. The duration is an experimental type. We have it in the standard library since 1.3.50 to represent a duration amount. It's actually unitless, so it doesn't have any particular duration unit tied to it, but it can be expressed as a number in any given duration unit, for example, in seconds, in minutes, in hours, or as a combination of them, and that result can be shown in the UI. A different situation is when you're making a chat application and you want to know how much time has passed since the last reply, and if that time is large enough, you want to show it as some number of days or a month ago. Probably you can find a duration between the last reply moment and the current moment, and just convert it somehow to days or month. There are several problems with this approach. First, months and years can have different lengths in days, so we can't just take any duration and convert it to a number of years or months. We need to know how long the particular months or years were between these two instances. And for that, we need to know what local date and time components this instance have. The second problem is that a day is not always 24 hours, as we have seen in the daylight saving time examples. It can have less hours when one is skipped, it can have more hours when one is counted twice. So the operation we want to perform with this instance needs to account for these daylight saving time effects between them. And to do that, we'll take the first part of this advice by Stephen Colburn and introduce the function until, which takes a time zone, converts this instance to local date times and in that time zone and calculates the duration between them expressed in a specified datetime unit. There are plenty of predefined datetime units from centuries to nanoseconds, but for these three units, we have handy shortcuts: days until, months until, and years until. Now imagine you want to show a countdown timer that updates every second and show how much time remains to some future event or has passed since some past event, for example, since the moment Kotlin 1.0 was released. And that time should be displayed as a mix of different units. We can represent the moment of that event as an instant. I did some historical research and found that Kotlin was released on the 15th February 2016 at 6 minutes past 13 UTC. So how can you do it? Again, you have the current instant, the instant of the event, and now you use period until function. Instead of an integer number, it returns a datetime period structure having the length of the interval between the instance expressed as a mix of normalized components: years, months, days, and so on up to nanoseconds. Using these components, we can get the desired string result. But what if you don't know the precise moment of an event and only know its date? Not a problem, you can use a similar period until function to find a period between local dates. Return type date period is a subtype of datetime period. It has only date-based components, and all time-based components are fixed to zeros. Now I'd like to show you how Kotlin language features help us to design aspects of the datetime API. For example, when you do a lot of conversions from an instant to local datetime and back, you may notice that constant passing time zone parameter becomes repetitive. What can we do about it in Kotlin? We can extract that time zone to a context as an implicit receiver with our scope function with, and now call to instant local datetime without passing that time zone explicitly because it's taken from the context. How does this magic work? It's possible thanks to having to local datetime and to instant extensions defined as members inside time zone class, so-called member extensions. This is pretty sleek, but unfortunately, it's not so extensible. All such extensions have to be declared as time zone members, and because of that, we want to stop on these two functions declared in such a way for now. So for other operations that require time zone, you still have to pass it explicitly. Then datetime unit type. It specifies in which unit we get the result of until function operation expressed, or in which unit the number provided to plus function is expressed when we are adding a number of units to an instant or a local date. There are plenty of datetime units predefined: years, months, days, time-based units such as minute, hour, and so on, more elaborate units such as a week, which is 7 days, or a quarter, which is 3 months. One can think that it's just an enum with a fixed set of values, but actually these predefined units are just constant properties in the datetime unit companion object. If we want, we can declare our own datetime unit as a multiple of an existing one. For example, if you need to express a duration between two instances in 4-week intervals, you can multiply the week time unit by 4 and use the resulting time unit in the until function. This is possible due to times operator being declared in datetime unit, and int produces another datetime unit which is a multiple of that. Another aspect of datetime unit class is that its design helps to prevent problematic operations. Remember that case with adding duration to a local date in JavaTime that results in an exception only at runtime? In Kotlinx datetime, you just can't add 1 minute to a date, either using the plus operator or the plus function. The first is impossible because there's no such operator overload. It takes local date time and a duration. The second is prohibited because local date plus function takes not any datetime unit, but only datetime units that are date-based. Datetime unit is a sealed class that splits to date-based units such as day, month, year, and time-based ones. And minute unit is clearly not date-based, so it can be used here. Okay, let's take a moment to recap what we know about the library so far. So in the library, we have types to represent temporal values. We have date and time arithmetic operations such as duration, until, plus, and minus, and some helper types that are used as parameters or return values in these operations. But what to do if you have a use case which is impossible to achieve so far with the provided set of API? First, it's important to report it to the library issue tracker on GitHub. Then you still may have luck with the platform API. But to use it, you don't have to rewrite everything to the platform types. In JVM platform, we provide the conversion functions from our Kotlinx datetime types to JavaTime types. You can convert a value, do the desired operation in JavaTime domain, and convert the result back to Kotlinx datetime types. For example, if you want to format an instant in such a format that we have seen in HTTP requests and responses, you can use this RFC 1123 datetime format instance of the datetime formatter class from JavaTime. But it requires JavaTime zone datetime on input. So first you convert Kotlinx datetime instant to JavaTime instant, then convert it to zone datetime with add zone function, then pass it to that datetime format. In Apple platforms, we also have the similar converters to platform foundation types. For example, you can convert an instant to NSDate or local date to NSDate components in order to format them. How to try this library in your project? In a multi-platform project, you can declare just one dependency in the common main source set, and Gradle will take care of finding a relevant variant of the library for each platform you have in your project. If you want to know the details of how this magic works, I recommend you listen to the talk by Dmitry Savinov the next day. And in a single platform project, you can declare the same exact dependency in the dependencies block. We have released Kotlinx datetime library 0.1 version. Maybe it will be a later version at the moment of the talk, but it's definitely not a final version and not the end of development. I'd like to share what we have in the near-term roadmap. First, we want to provide an integration with Kotlinx serialization library. In a distributed multi-platform application, it's a fairly common task to serialize data in one part of the platform system and then deserialize it in another part. So we'd like to provide some ready-made serializers out of the box. Then we want to support such a certainly important feature as formatting and parsing. At first, it will be without internationalization, so it will support just English names for month and weekdays. We also want to support ranges and progressions of temporal values so that you can iterate them. And finally, we want to provide a way to embed a time zone database. Why is it important? We rely on Platform API for working with time zones, and due to that, it may be absolutely unpredictable which version of time zone database is going to be used in the platform where your application runs. So you can get different results of operations involving a time zone from what you have expected. This could be mitigated by bringing a particular version of time zone database embedded with your application. So please share your feedback, because at this point, it can considerably affect the direction of our development. You can file requests for the missing API in the GitHub issue tracker. You can use the Kotlin Lang forum for discussions, and in the Kotlin Lang Slack, we have dedicated Kotlinx Daytime channel, and we'll be glad to see you there. So, thanks for watching, and have a good time with Kotlin.